I hope all of you can see my screen, which is in front of you. And on the screen, which is what is written is finitely additive set function, something probably you are not able to connect with probability. Okay, now in every class, if you have attended any, the basic problem which we discuss to know the fundamentals of probability is a coin tossing problem. But what the teachers do not mention is about the intricacies of this coin tossing problem, which the intricacies which are hidden inside it. And also, we do not put emphasis on sample space. When we will do conditional probability, then you will see that the sample space plays the most fundamental part in studying probability theory. And if sample spaces are not known, then you cannot calculate the probability. But today I'm going to break the notion of calculating probability of a particular event. And for this, the notion, you think that when we do, say for example, coin tossing, we toss the coin, when we calculate the probability by the formula that favorable number of case by total number of case, that notion I'm going to break today. Okay, my declaration is that I do not calculate probability. We do not calculate probability. So what do you do actually? So to understand that particular part, I'm going to start my presentation with the note, which starts with the topic of finitely additive set function. I'm not going to do any kind of board work right now because that note has been prepared by me. You can see it is a handwritten note. So I'm going to present this. And don't have to write anything in your copy. You just sit quietly and listen to me. After the class, I will share the note with you. You know very well. Okay. Now, let me save your chat because it is also very important. Yeah. I can see 60 participants. I hope that all the participants have written their roll numbers in the chat box. First definition, which I like to mention, is called the finitely additive set function. So what is that finitely additive set function? It is written that in this case, we first of all take a collection of sets, a collection which we denote by script letter A, script A. In this script letter A, we consider the elements which are themselves sets. Okay, so therefore it is written that the script A is collection of sets. So it is a set of sets. So on one hand, we are containing this collection, okay, which we call as domain, because you can easily see that I'm going to define a function from this particular collection to the set of real numbers. On the other hand, we have the set of real numbers. Okay. Now, if we can define such a function where the elements are itself sets of points, and these sets are taken from a collection, and after applying the function on this particular set, if we get a particular real number or any real number, okay, then that type of function is actually called a set function, which I have tried to diagrammatically represent below, which you can see probably that in this diagram, I have defined the collection. I have drawn the collection. I've drawn the script A by this this particular portion. It's not a circle. It's just a figure in which I have this particular figure contains, it's the collection. It contains every possible sets inside it. A1, B1, A2, B2. These are not elements. These are actually sets. And from this collection, I'm going to define a function, and that function is, according to my definition, is a real number. So therefore, I have drawn a real line. So if you choose any particular set from here, say A2, and then if you apply the function f on A2, you are going to get the real number. Very abstract. Okay. So to make this particular thing clear to you, let me consider that this A1s, all the A1s over here, or the B1s, whatever you say, these A1s are all the triangles we are considering. Okay. So triangle is what? If you consider a triangle contains 3 vertices. So you can consider that 3 vertices, 3 lines, when we join them together, we get a triangle. So A1 contains the set A1 contains this vertices and these sides with which we can construct the triangle. So we are actually, when we choose A1, we are actually choosing the triangle. And when we calculate the area, this area is my function. So when we calculate the area of the triangle, okay, which is given by the formula half into base into our altitude, then what we get? We get a real number, okay? And therefore, area is a kind of set function. Area is an example of set function. For example, if we consider a set B2, I'm not talking about this collection, because in this collection, if you're considering all the A1s and B1s, all of them are triangles. Then if we're considering triangles, then all the A1s and B1s are triangles. If similarly, if you draw another collection, script A, where all A1s and B1s, they represent some sets which contain persons. So for example, B2 is a set, okay, and which comes from a different collection. And B2 contains, say, one of the students of my class, which we name as person B. And if I calculate the height of that person B, then we can say that when we apply height as a function on the set B2, B2 contains a single element, then that particular height is also a real number, and therefore height is also a kind of set function. And you can cite many more examples like that. Okay. Now, set functions have a kind of property which is very important. It is saying that if I can define a set function like this, say for example, f from the script A to the set of real numbers, then this set function will be called a finitely additive set function. If you choose two sets from this collection, script A, which we denote by capital A and capital B, and we take their union, because you know that when we consider two sets, they can be combined together with the help of the operation union. So when we take the union of these two sets and we apply the function on it, okay, then f of A union B gives you the sum total of the function when applied on the set capital A and the function when applied on the set capital B separately. If such a thing happens, then we call this kind of function as this kind of set function as finitely additive set function. One condition is obviously there, that if this is to hold, then from your script A, you are going to, the elements which it contains, they must be disjoint. I mean, you cannot consider any particular type of function, any particular type of two particular sets which are not disjoint, and you are going to get this finitely additive property. You are not going to get finite additive property over there. So one basic condition is that if this property is to be held, then all the sets chosen from that collection must be disjoint. And not only this, in the collection script A, if capital A and capital B are present, then A union B should also be considered to be an element of this collection script A. Okay. Now, from this definition, we can easily see that area and height, as we have mentioned in the above paragraph, these area and heights are actually finitely additive set functions. Take two persons, okay, and you come one person, a set of one person, person one, and another set of persons, person two. If you combine them, person one, set of person one union set of person two, their height will be equal to sum total of the height of person one and sum total of and the height of person two. And this is the same case happens with area also. Okay, so area and height they are set functions and they are finitely additive. But here in this particular class, we are least interested about area and height. We are not going to, we are not here to study these things. We are going to study something else. Next definition which is very important, is called Boolean algebra of sets. Boolean algebra is a topic which we'll be learning in the fourth semester. Okay, so here I'm going to give you a glimpse of Boolean algebra. What Boolean algebra is? In the previous paragraph, we have considered any set, any collection script A. Now we are considering a special type of collection script A where the collection script A is non-empty. Okay, it contains some sets. Then, and what type of sets it's containing? Suppose we have an universal set capital S, and all possible subsets of universal set capital S is considered to be inside the collection script A. Again, I'm saying we have a set capital S, which we call as universal set, and all possible subsets of this set are considered to be contained in the collection script A. Okay, then this particular class capital A will be called Boolean algebra. This class will be called Boolean algebra. Boolean algebra is a class of sets, a special type of sets. We call it Boolean algebra if the following operations are satisfied. What type of operations are being satisfied in this particular case? That for every element capital A and capital B to be which are taken from the collection script A union B should also be present in the collection, and A complement should also be present in the collection. Okay. So if these things happen, then we call them as Boolean algebra. Now, let me come to the important part, and which is relevant to our topic. Definition of probability for finite sample space. Sample space, you know, sample space is collection of all possible outcomes. We used to call like that. Now we are going to define probability in a different way. Let this B denote a Boolean algebra whose elements are subsets of a given finite set capital S. Okay, a set function capital P, script P, is defined on the Boolean algebra B. This script P is called a probability measure if it satisfies the following properties. What are the properties? So the script P, the first property which is satisfied by the script P is that it should be finitely additive. Okay, if you choose any two elements, any two sets from the Boolean algebra, any two disjoint sets from the Boolean algebra, then probability of those disjoint sets, union of those disjoint sets, will be the sum total of their individual probabilities. So the P, the probability which we call as probability measure, is actually has to be finitely additive. This is the first condition. The second condition is that if we consider any set from this collection script B, which is Boolean algebra, then probability of that particular set will always be greater than or equal to 0. And if we consider sample space S from this Boolean algebra, because you know the sample space is actually the entire universal set, and this is the union of each individual subsets, and to be in Boolean algebra, that universal set has to be present also. So if you consider that S, that universal set from the Boolean algebra B, and if we apply the probability measure on it, so probability of S will become 1, which we actually call a certain event. Okay, so sample space, total sample space is a certain event. Okay. Now I can cite another example to explain this thing. Suppose you are tossing a coin, and the probable outcomes are capital H and capital T. So you are considering the set containing head and the set containing T, and their union will be the sample space which contains both head and tail. Now, if I ask you, and you know that set containing H and union set containing T gives you the total sample space. Now, if I ask you what is the probability of getting head or tail, if you toss a coin, you will say that, yeah, actually you are talking about the total sample space. So the probability is definitely has to be 1. So therefore, in this way, we are actually defining, first of all, we have started with a set function. Then we have defined that when a particular set function is finitely additive, after that, we have considered a special type of set function, which is a Boolean algebra. And Boolean algebra uh, has to have this kind of properties. If you choose any two elements from this collection, then their union must also be present and their complement must also be present. And if this is so, and if we define a kind of function which we call as probability measure, and that probability measure satisfies these following three properties, then the triplet universal set along with the Boolean algebra, along with the probability measure, this triplet is often called probability space. You have already learned vector space in the last semester. In vector space is also a kind of triplet where a set, a non-empty set was there, and addition operation was there, and multiplication operation was there. Here also you are considering a triplet where, first of all, and you cannot just interchange. I mean, you cannot write, okay, BPS is a probability space, or you cannot write PSB is a probability space, or PBS is a probability space. You have to write SBP. This is the sequence, SBP. That means what? To define probability, first of all, you have to be sure that you have the sample space at hand. Okay, so if the idea of the sample space, how many elements are present inside the sample space, are clear to you, then you can construct the Boolean, accordingly you can construct the Boolean algebra, and you can define the probability measure on it. Now, if this S is missing, if this sample space is missing, then this Boolean algebra, this probability has no meaning. Actually, Boolean algebra will not be able to, we will not be able to construct the Boolean algebra. Now, say for example, suppose you want to calculate the probability that a teacher, when gives private tuition, he actually earns more than 30,000 per month. Now you cannot calculate what is the probability that a private teacher who gives private tuition earns more than 20,000 per month. You will not be able to calculate the probability, because in this particular case, the total sample space is not known to you. You do not know what is how many elements are present, how many private tutors are present, and what are their incomes. That total sample space is not present, and therefore you cannot construct the Boolean algebra, and therefore you cannot calculate the probability. Now, these points A, B, C, these points are actually called axioms. Now, axiom in mathematics, axioms are actually known as pillars. Axioms cannot be proved. Okay, axioms cannot be proved. They can only be assumed. One of the mathematicians once said, his name is Mahan Maharaj from Tata Institute of Fundamental Research. He once said that axioms can also be proved. We say that it cannot be proved because we are not able to prove it, but it's not a universal truth. So right now at this moment, I'm taking your class. Till date, these 3 points are actually axioms. Okay, because they cannot be proved. You can assume on, and this is the 3 pillars on which the total probability theory is based upon. Now, if you omit one particular pillar, okay, then the entire structure will tilt to that side. Okay, and you will not be able to define. You will be able to define something, and you will not be able to define other things. So these 3 axioms are very fundamental, and in some books you will see that this approach which I've shown to define probability space and probability measure, this approach is called axiomatic approach to probability. And in our course, we will often use this axiomatic approach and their respective properties. Okay, so this is all about probability space, where we first consider the universal set. That means the sample space. From set theoretic approach, we call it universal set. From probability theory perspective, we call it a sample space. Then we construct the Boolean algebra, and then on this Boolean algebra, we define the probability measure, and we call this triplet as probability space. Now, when I write note, okay, When I prepare notes, sometimes I got distracted and I actually do some sort of mistakes, okay, in writing. So here also I have done a very small mistake, which I will ask you to rectify. Uh, I'm telling you what is that. You can note this particular point on your copy if you have it. And when you learn, you will rectify that thing. Now it is a handwritten note, so I was not able to rectify that silly mistake. You will understand what mistakes I'm talking about, what mistake I'm talking about. So what I'm doing right now is that I am actually moving back to the same old coin tossing problem, which teachers often do to explain probability, favorable number of case by total number of case. Now, what is happening? Very carefully listen to me what I'm telling to you. Now I'm tossing an unbiased coin. So underline, mentally you underline this word unbiased coin. I'm tossing an unbiased coin. When I toss an unbiased coin, then this capital S is actually the sample space, because I'm sure that if a coin is tossed, what probable outcomes can occur. So we know that these outcomes are H and T. Okay, no problem with that. Now, once we get this these outcomes, so after that, my next job is to construct the Boolean algebra. So I am constructing the Boolean algebra now. Now, what is Boolean algebra? Boolean algebra is a collection of sets, which contains subsets of the given universal set capital S. Okay, no problem. So I am going to consider all the subsets of this sample space capital S. Now, my mistake is that, when a particular set is containing two elements, then the power set of that set contains 2 to the power n elements. So this Boolean algebra, being a collection of subsets of capital S, must contain 4 elements. I have only shown here 2. Now, the missing subsets are what? Phi and the total sample space. So you note down those things over here in your copy, that this Boolean algebra has to contain 4 elements: singleton H, singleton T, then a collection containing H and T, that is the sample space capital S, and Phi. Four things will be present. Now, Phi means no outcome it's impossible event. Now, when we toss a coin and the coin is standing on its edge, okay, just like it happened in the case of when Amitabh tossed the coin in Sholay, it stands on the edge. So this type of thing is impossible. Generally, they are discarded. So I'm least interested about Phi. Anyways, no problem, but Phi has to be there because you are going to construct a Boolean algebra. Now, if you ask me, sir, why, if I do not consider, do not consider S inside Boolean algebra, capital B, what will happen? I'll say that it is just a collection. It is not a Boolean algebra. So, for example, in Boolean algebra, what we must get? We must get that if a set is there, if two sets are there, their union has to be present over there also. Now you see, you take this collection H and you take this collection T, you take their union. Their union is the total sample space S. Now S is not present, so capital script B is not a Boolean algebra. So that is my mistake, which I didn't write. Now another thing is that if you take any set, its complement must also be present over here. So okay, then you take H, its complement is T, present. T, its complement is H, present. Now you know that HT is also present over here. So HT's complement is what? Phi. The phi is not present. So that is my mistake. And if you have phi, then its complement is the total sample space. So actually in this Boolean algebra script B, there has to be 4 elements. Then we can say that it is the Boolean algebra of sets. Assuming that H and T are equally likely. Now these outcomes are equally likely. Why they are equally likely? Because I have assumed that this coin is an unbiased coin. So probability of head will be half. If you say that how is it so, then I'll say, okay, favorable number of case by total number of case. Think like that. And probability of T is half. Now, if you ask any layman who is not uh, familiar with this formula of classical definition of probability, if you ask him that what is the probability that when a coin is tossed, what is the probability of getting head and tail, he will also say that the chance is 50-50. Now, on the back of your mind, you are always assuming that, yeah, okay, this coin is unbiased. Now, the important part is that how can you justify that this coin is unbiased? There is no way to justify that because you do not know what factors to be checked to declare a coin to be an unbiased coin. Okay, so there, when I say the coin is unbiased, that means we just assuming that, yeah, okay, maybe they are unbiased. And when we consider that the coin is unbiased, then we all obviously these outcomes are equally likely. Okay, so they're equally probable, and therefore we call it 50% and 50%. Now, suppose I'm tossing a coin. Now, I'm clear about the sample space. It contains two elements, H and T. I'm constructed the Boolean algebra. Okay, and but you have not declared that the coin you are tossing, you do not know whether it is biased or unbiased coin. You do not know about it. Okay, there is no way by which you can know that whether the coin is biased or unbiased. Then what will happen? Will you write probability of H equal to half and probability of T equals to half? No, no. Now, you can ask me, what can I write then? Now, if I ask you the same question over here, because if it were a physical class, I could have asked you and I could have learned from you. But since we have no time, so I am actually answering my own question. So being you, I could have said, some people could have said that, okay, the probability of head will be then in that case 1/3 and probability of tail is then 2/3. Because you know, on the back of your mind, you know that the sum total of the probabilities always has to be 1. You can also say that probability of head in that case is 1 and probability of tail in that case is 0. Probability of tail is 1, probability of head is 0. Now, in general, if I collect all your answers together, I'll say that, okay, do not say like this because there are many real numbers. In real number set is infinite. You say that probability of head is small p. Small p is a real number. Probability of tail is small q. Small q is a real number. And p plus q is 1. This is the condition. Now you have to consider p lying between 0 and 1 and q lying between 0 and 1. You are choosing the real numbers in this manner. And inside 0 and 1, there are infinitely many real numbers. So if the coin is, you are not declaring the coin is biased or unbiased, then we'll be at a loss and we'll say that, okay, anything can be probability. But when we say the probability is half and half, that means on the back of our mind, we are assuming that the coin is unbiased and the outcomes are equally probable. Okay, and you see, when we consider this probability as, when we consider this coin to be unbiased, probability of head is half and probability of tail is half, then probability of H plus probability of T, that is half plus half, it should be the probability of H union T by the rule of finitely additive set function, and that should be equal to 1. Okay, so therefore this is very important, and this particular part, when we are assuming something that this is true, this is actually, in statistics, this thing is actually called hypothesis. In the module 5, module 4, you will see that module 5 will get to see that there is a chapter called hypothesis testing. So actually right now you are learning about probability, but actually you are learning how to construct the hypothesis. So our basic goal is to check the hypothesis we construct. Here our hypothesis is that we have considered, whenever we say that probability of getting head and tail is half and half, always we consider that they are coin is unbiased and they are equally probable. But this is not always true, because there is no way by which you can justify whether a coin is biased or unbiased. So probabilities are, my conclusion is that probabilities cannot be calculated. They are not calculated. Classical definition by which actually we learn just for its simplicity. After that, we say that classical definition has its own limitations. Okay, if classical definition could have solved all the problems, then the probabilities, there will not be able to there will not be anything like probability theory. So it's just a kind of basic idea. Okay, these things happen for certain cases. Probabilities are not calculated. We assign probabilities. We put the values. We put it. We do not calculate it. So just like you put the probability of head is equal to 1, you think when it is biased, and probability of tail equal to 0. Somehow you think that probability of head will be a certain event. So you actually are not calculating, or putting things. Okay, so that idea which you had in your mind, that we calculate probability, you just take it out from your mind and stick to that. Okay, from this point onwards, we shall be learning probability from this axiomatic viewpoint. Okay, now I'll ask you to write this particular question in your copy. Okay, this question is, what is the question? I'm reading it out for you. I'll be explaining this problem, maybe not in this class, maybe in tomorrow's class also, but you just write it down. Question goes, because after that we'll be doing some kind of board works. So the question is, let capital A and capital B be two events, neither of which has probability 0. Prove or disprove the following statements. Okay. First of all, if capital A and capital B are independent, then capital A and capital B are disjoint. If capital A and capital B are disjoint, then capital A and capital B are independent. This is a very important problem, which I've chosen from the book of known as Calculus by Tom A. Apostol. Okay, volume 2. So this problem is a very fundamental problem. We shall be discussing it, but I ask you to note down this particular problem. Time is also running out. Okay, let us try to do this particular problem. Let us try to, in this minimum time, let us try to do it. Let me do the problem number 2. Problem number 2 means, first of all, problem number 2 means if capital A and capital B are disjoint, then we have to prove that whether they are independent or not. Now, two events are said to be independent. Capital A and capital B are independent events if you write in your copy, the probability of A intersection B is equal to probability of A into probability of B. Then we say that if the events are independent, then we get this particular formula. The probability of A intersection B is equal to probability of A into probability of B. Now, when we say that the events are disjoint, two events are said to be disjoint when we say that A intersection B is equal to phi. It's impossible. Okay, so here in this particular problem, we actually like to know whether independentness implies disjointness, whether disjointness implies independentness. Okay, and this particular problem is also very important for the understanding of probability theory. We have less than 1 minute, and I am stopping my video right now at this point. In the next session, I'm going to do some kind of board works before we discuss this particular problem. Okay, so I'm stopping here right now.